Imagine holding a teaspoon in your hand. Now imagine that teaspoon weighs more than every car, truck, airplane, and ship on Earth combined. About 4 billion tons. Sounds impossible, right? But that's exactly what would happen if you managed to scoop up just a tiny bit of material from a neutron star. This isn't some science fiction fantasy, it's real mind-blowing physics. But here's the twist. Scientists say these tiny remnants of dead stars don't just break the rules of density as we know them, they completely redefine them. And it doesn't stop there. These cosmic powerhouses, forged in the heart of exploding stars, can spin hundreds of times per second, emit beams of radiation brighter than anything we've ever seen, and even warp space and time around them. But what makes neutron stars so mind-boggling? How did they get so dense? And why does this story involve some of the most extreme conditions in the universe? You might think, okay, a teaspoon weighing 4 billion tons sounds impressive, but how is that even possible? Trust me, once you dive into the science of neutron stars, you'll never look at the universe the same way again. To understand why neutron stars are so incredibly dense, we need to rewind the cosmic clock to their birth. Every neutron star starts its life in the same dramatic way, as the fiery remains of a supernova. When a massive star runs out of fuel, its core collapses under the force of its own gravity. But here's the catch, the collapse doesn't stop. Gravity crushes the core so intensely that electrons and protons are forced to combine, forming neutrons. The result? A sphere of neutrons packed tighter than anything else in the universe. But just how tight are we talking? Imagine squeezing the entire Mount Everest into the size of a sugar cube. That's the kind of compression we're dealing with. And it doesn't just stop with density. Neutron stars are extreme in every sense. They're small, about 20 kilometers across, yet their mass is up to twice that of our sun. Think about it. Something the size of a city holding the mass of 2 suns. It's like taking all of New York City, condensing it into a marble, and then making it so heavy it could sink to the center of the Earth in seconds. The real question is, how can something like this exist without collapsing into a black hole? And how does this ridiculous density affect everything around it? Here's the challenge. Neutron stars shouldn't even make sense. The laws of physics as we know them are pushed to their absolute limits inside these objects. For one, there's the issue of gravity. Gravity on the surface of a neutron star is so strong that if you were to drop an object from just a meter above the surface, it would hit the ground at 7.2 million kilometers per hour. That's about 2% of the speed of light. But there's more. The matter inside a neutron star is unlike anything we encounter on Earth. Scientists call it neutron degenerate matter, and it's so dense that just a single cubic centimeter of it weighs about 400 million tons. That's equivalent to the weight of Mount Everest, but in something the size of a sugar cube. Now here's where things get tricky. Scientists can't directly study neutron stars. They're too far away, and their conditions are impossible to replicate on Earth. So how do we know so much about them? Neutron stars form in the aftermath of a supernova, the explosive death of a massive star. During the explosion, the outer layers of the star are ejected into space, leaving behind a core. If the core is massive enough, about 1.4 times the mass of our sun, it collapses into a neutron star. But this collapse isn't like anything you've seen. The star's atoms are crushed under intense pressure, forcing protons and electrons to combine into neutrons. These neutrons, in turn, pack together so tightly that the core becomes a giant atomic nucleus. So why doesn't a neutron star collapse into a black hole? It's all thanks to neutron degeneracy pressure, a quantum phenomenon that resists further compression. Think of it like this. Neutrons are stubborn. They can't occupy the same space as one another. This resistance creates enough pressure to counteract gravity, preventing the star from collapsing further. But there's a limit. If the core's mass exceeds about 2.16 times that of the sun, even neutron degeneracy pressure isn't enough. The star will collapse into a black hole, where gravity reigns supreme. A density. As we've covered, a teaspoon of neutron star material weighs 4 billion tons. That's Earth's surface gravity. The gravitational pull is so strong that escaping it requires speeds over half the speed of light. But spin. Neutron stars can spin up to 700 times per second, making them some of the fastest spinning objects in the universe. Magnetic fields. Their magnetic fields are trillions of times stronger than Earth's, capable of distorting atoms into needle-like shapes. We may not be able to touch neutron stars, but we can observe them through telescopes. Some neutron stars, called pulsars, emit beams of radiation that sweep across the sky like lighthouse beams. These beams allow scientists to measure their properties and learn more about their extreme nature. Now let's get to the heart of the matter. What does all this mean for our understanding of the universe? Neutron stars challenge everything we think we know about matter, gravity, and the limits of physics. They exist in a realm where quantum mechanics and general relativity collide, a place where the rules break down. And here's the kicker. Studying neutron stars could unlock the secrets of black holes, the early universe, and even the fundamental building blocks of matter. These tiny cosmic leftovers are like laboratories for the most extreme physics imaginable. Neutron stars are a testament to the universe's capacity for extremes. Born from the fiery death of massive stars, they condense matter to unimaginable densities, warp space and time, and push the boundaries of what's physically possible. A teaspoon of neutron star material may weigh 4 billion tons, but its significance in unraveling the mysteries of the cosmos is even heavier.